This is section 3.5, number 1, a case of repeated eigenvalues. I'm not going to solve for the eigenvalues. I think we're all comfortable with that, but if you set up the characteristic polynomial, you should find that lambda is equal to -3. The formula for the eigenvector is, as we always do, whether it's a real number or a complex eigenvalue, A times the eigenvector will equal the eigenvalue times the eigenvector, and this gives us our two equations. The first equation is true for all x and all y, no restrictions. The second equation will only be true if x is equal to 0, so that is our one and only restriction. Our eigenvector is anything that has a 0 component for x. 0, 1 does the job. But to draw the direction field is very difficult. We can do it once we have a phase diagram, and that's actually easier to draw. So we're going to start with that. Our eigenvector is 0, 1. That's pointing along the y-axis. That means any vector in the y direction is a possible eigenvector. This is our eigenvector direction. And I'm going to draw two separate pictures because I think this becomes a little easier to do when you realize there really are only two cases. The solutions, remember, when we write them out, are going to look like this. E to the minus 3t, some initial condition, plus t e to the minus 3t times v1, where v1 points along the eigenvector direction, pulling out the e to the minus 3t. We have v0, wherever it is we start, t v1. And as I've said in class and mentioned in our book, for large values of t, large positive values of t, and large negative values of t, this is the dominant direction. This is the driving factor when t is large and positive. This is going to 0. But in what direction? Well, as we add these two things together and then multiply by something that's going to 0, this direction will dominate. This term will dominate. And so we will always approach this line as we go to the origin in a direction that's parallel to the eigenvector direction. And similarly, for large negative values of t, we will be coming into the origin parallel to v1. So I'm going to use blue on the top one. What I'm saying is, suppose this is an initial value. We have two choices. We can be coming in roughly parallel to the direction, and then we have to turn and approach like this. Here's my initial condition here. That's one way it could happen. Or I'm going to place the same thing here. Or we're coming in this direction and then turning and approaching our 0 in this direction. These are our two cases. If we're in this case, I'll call this case 1. This is case 2. If we're in case 1 and I've accepted that this is a solution path, then I know what all the other solution paths look like. They all are going to come down and curve and curve. They're all going to cross that axis. They can come out wider and curve. And on this side, and by the way, this curve would be counterclockwise. I'm sorry, this curve would be clockwise. This is a clockwise rotation. We're coming down and then we're turning in a clockwise fashion. On this side, it would have to then be something like this. And again, these rotations are clockwise. So that's one possibility. Or if we approach our point with a counterclockwise rotation, then everything here has a counterclockwise rotation. It looks like this. We'd come in on this side like this and like this. So how do we determine, are we in case 1 or case 2? As I showed in the previous screencast, the secret is to do one thing, and that is to pick one point and look at the resultant when that has been multiplied by the coefficient matrix. So let's just take 1, 0 in this case. It's best to sort of stay on the axes. I want to stay off of the y-axis because when I multiply that by the matrix, I know I'll get something. It's an eigenvector direction. I know I'll get something along the y-axis. But here, let's just do a little analysis. So suppose this is 1, 0 right here and here. Let me use a different color. Let me use red. Here's red. Okay. Well, when I multiply minus 3, 0, 1 minus 3 times 1, 0. In this case, I'm expecting my x vector, so let me draw a little vector direction here. Poorly done, but something like this. I'm moving in this direction, and here I'm moving in this direction, right? In both of these cases, there's a negative x component. I'm moving to the left in x, I'm moving to the left in x, so I'm expecting to get a negative x component, and sure enough, when I do the multiplication, I get a minus 3. But in this case, the y component is negative, I'm pointing down. In this case, the y component is positive, I'm pointing up. When I do the multiplication, I get a positive 1 here. And so I'm pointing up, and so this must be so it must be case 2 that we are in, right? This is our this is what our phase plane must look like because it's consistent. I've picked one point and it's consistent with that drawing, and therefore everything else will be consistent. So this is not the case, and this is our phase plane. Now that I have C, it's easy to understand that I could just fill in little arrows everywhere and make a little direction field if I wanted to. But in general, I'm not going to ask you to make direction fields. It's too tedious. But I hope you feel comfortable that we could get a rough idea of drawing a direction field once we have the phase diagram. Part E asks you to sketch x of t and y of t graphs for the initial condition 1, 0, and I'll do that on the next page. When we're asked to make a sketch of x of t and y of t, we can, of course, look at them specifically. The initial condition is 1, 0. That's v0. The way we find v1 in the case of the double repeated eigenvalue is a minus lambda times I times v0. Do the math, we end up with 0, 1, which is consistent, that is in the eigenvector direction. So here's our solution. When we break it down, we see that the x component is just e to the minus 3t, and the y component is t e to the minus 3t. So we could use graphing calculators and make a sketch of these, but let's look at the curve itself and see if we can understand how to make a sketch from that. Okay. Here's the initial condition, 1, 0. Here we are at 1, 0. And this is where we are at t equal to 0. So So here I am, I'm going to draw x of t. And so at t equal to 0, my x value is here. And as t moves forward, it moves towards the origin. We'll never pass it because the origin is a sink in this case, and it attracts this all points to it. And so as time moves forward, we get closer and closer. If you look at this expression, e to the minus 3t goes to 0, never reaches it. And had I not known that it's exponential, I know that it's approaching 0 asymptotically. It'll never cross it. So it does make sense to draw a picture that looks something like this. However, it's also important to feel comfortable that before, for example, before t equals to 0, let's say we're right here at t is equal to 1, minus 1, right? And here we are, let's say at t is equal to minus 2. Well, the x values are moving out on the x-axis, and so I would just want to show something that is getting as at minus 1 and minus 2. I want to show something where the x values are growing, and that would be a reasonable graph of x of t. The y of t case, again, y starts at 0. Here we are at 0, at time 0. This is my time axis. Then what does y do? It grows for a certain bit, and then it comes right back down to 0. So y goes up and then comes back down. So as time moves on, it's getting bigger. It has some maximum, then it comes to 0 and approaches 0. Also never reaches it. As t moves forward, t e to the minus 3t goes to 0, never reaches it. However, before 0, at minus 1 and minus 2, it wouldn't be hard to see that this is what would be going on. The y values are negative. We're working our way down the y-axis. And so there are two rough sketches. These based upon these two are based upon this graph, or wouldn't hurt to be able to use your calculator. Okay, thank you.